Now, in your textbook, what we're going to cover today is covered in chapter 17. The acids and bases, we went up to 17.3 in your textbook. And now we're going to, I think this finishes that chapter. We talk about solubility and complex ion equilibrium. All right. Get that right. That's the right exam number too. There we go. So when we're talking about, remember last semester when we talked about reactions that produce the solid, precipitate reactions. And I had that chart, and you could take your cations across the top and your anions down the left-hand side and see which ones are soluble and which ones were not. All of those ones that were insoluble, you remember that chart with the grayed out squares? All the ones that are insoluble are in fact slightly soluble. Now we're going to figure out just how soluble they are using equilibrium. Okay. So, and I also mentioned when I started talking about equilibrium and the K values for equilibrium, they had subscripts, right? We did the last two chapters we did Ka for acids, Kw is special for water only. Keq is general, and it's usually in terms of molarity for any reaction. And then there's Kp, which is equilibrium constant when you all gases and you're using pressure values like atmospheres. Well, this one is the next one that we're going to study is Ksp. Sp stands for solubility product. The reason it's solubility product is this. If you have let's just take a generic. We got a cation and anion makes a salt, right? And this is going into solution, and it's in equilibrium with its ions. So we have that in aqueous solution, and we're going to stick to aqueous only. All right? So there you have a generic solubility of an insoluble compound. Right? We used to call it insoluble. We know we get a little bit over here. So if we write the K for that one, then you would be tempted to write like this, like that, over this. Correct? But we know from the rules that solids don't change concentration. So the solid goes out. And now all we have is just the right-hand side of the equation, like our water. Right? We leave water out, H2O, because it's a liquid, not included. This is why it's called a solubility product, right? The product is a number times another number. So a solubility product is always just this side of the equation. And of course, if it has coefficients here, then they would become powers. All right, and there's our example. That particular example is bismuth sulfide. And when you write the solubility product for bismuth sulfide, you have bismuth, the 3+ ion to the second power, and the sulfide to the third power. So remember, solubility product is one of those equilibrium constants, and they are constant. As long as the temperature is constant, those values are constant. Now, what do we mean by solubility? Well, let's see. We had bismuth sulfide, right? 2 and 3 solid. What's the solubility of that compound? The solubility is how many moles of that will go into solution. Okay, and that is usually in terms of moles per liter, which is molarity. So we say of that solid, how many moles of it will go into solution? Now, the question here, as given in the slide, is if you know that the KSP of one reaction, right, of this reaction is greater than the KSP for a second reaction, what does that mean? Well, it means the calculated value, the solubility product with its powers and all that stuff, is bigger than this one. But the question is, does that mean that the solubility is bigger? And the answer is no. Because the way you calculate it, including the powers, will give you a different value for solubility than it is for the KSP. So I think examples would help here. Okay. Sometimes we say solubility in terms of moles per liter, and sometimes we say grams per liter. That's another possibility. All right. So our example here at the bottom is the KSP for sodium chloride is equal to the solubility squared. Now I need to work these out and show you how you determine that solubility. But the sodium phosphate KSP is 27 times S to the fourth. So those two values, the KSP for sodium phosphate will be 27 squared of the sodium chloride, but we don't know what those S values are yet. So we have to calculate that. Calculate the solubility of silver chloride. Silver chloride. Was that silver chloride? No, sodium chloride. Silver chloride in water if it has a KSP of 1.6 times 10 to the minus 10. All right, here's what we do. And remember I told you that the ice table was going to stick around for a while. Yeah. Okay, silver chloride. Let's write the equation. Silver chloride solid is in equilibrium with silver ions in aqueous solution and chloride ions in aqueous solution. And the KSP, let's see, KSP, let me erase these right here. The KSP is equal to concentration of silver, concentration of chloride, and that's equal to 1.6 times 10 to the minus 10. That's everything that's been given to us. What they want us to do now is to calculate the solubility in terms of how much of this goes into solution. All right. All right, there's our equation. Right, now how did we end up with that? That's where the ice table comes in. Right, this is not going to be in the ice table, so I'm going to put the ice over here. When we first put this into solution, there's nothing there. Right, so the initial concentrations here are 0 and 0, obviously. Okay, so what's the change? Well, we're gonna add some here and add some here. Right? What does that mean, though? This is we're gonna have X molar here and X molar here because they're equal 1 to 1, but they're also 1 to 1 here. So X means that this is minus X, which that is the solubility. Right? How much does this lose when it put it in water? Okay, so it's convenient that X is our solubility. Right, so now we get X here and X here. So if we substitute X and X here, this is X times X equals 1.6 times 10 to the minus 10. Right, so X, that's X squared. X equals the square root of 1.6 times 10 to the minus 10. And that should be the solubility error. 1.3 times 10 to the minus 5. Since this value was derived from molarity, this is in molar. That's the solubility. 1.3 times 10 to the minus 5 moles per liter is how much of that will go into solution. How about silver phosphate? All right, I'm going to leave that one up there for silver chloride. And let's change this to silver phosphate. All right, this is 3 minus. This is a 1 plus, so that means we need 3 of those, correct?
Yeah.
Okay, that's our solid. All right, so now when any of this goes into solution, we get 3 of these and 1 of these. Okay, so again, we're starting off with nothing. If one of these, if we say minus X here, let's see, well, that's not where it goes. Down here, minus X. If we lose one of these, which would be an expression of the solubility of that compound, minus X, then we're going to get 3 X's here, right? For every one of these, you get 3 of these. Correct? Okay. And for every one of those, you get 1 of these. Okay, so now at equilibrium, we have 3X and X. And if we write the expression, KSP for this expression is solubility product, silver, and this is to the 3rd power, and phosphate. Okay. Now, KSP is 1.8 times 10 to the minus 18. 1.8 times 10 to the minus 18 is the KSP. And this concentration is 3X to the 3rd power, and this one is X. Okay? Or, I'll tell you what, it may be easier to understand if instead of X, we write this as S, as solubility. That's the solubility. Then each one of these becomes an S. Okay. And this becomes an S. So when we solve for S, then we can say S is the solubility. All right, so this is, what's 3 cubed?
27.
27, yeah. 27. S cubed times S is S to the 4th. Right? So S then equals the 4th root of 27 divided into that. Right? Right? S to the 4th will be this divided by 27, and then S would be the 4th root of that. Okay. So, where's my calculator? I'm going to do 1.8 to 10 to the minus 18. You turn divide by 27. Okay, now how do I do the 4th root in my calculator? It doesn't have a 4th root, so the 4th root of thing is like the value to the 1/4 power, right? Okay, so I'm going to say 0.25, and that's the power. So I should get S equals 1.6 times 10 to the minus 5 molar. Okay. Let's see if that came out right. Yeah. So if we look at the KSPs here, this one is for silver phosphate, and this one is for silver chloride. Oh, excuse me, that's not right. I'm comparing the, not the solubilities yet. Let's compare the KSPs. Here we go, KSPs. So the KSP for silver chloride is 10 to the minus 10th, and for silver phosphate is 10 to the minus 18th. And if we made the wrong assumption, we would say, well, this must be more soluble, right? But if we look at the solubility calculation, this is 1.3 times 10 to the minus 5th, and this is 1.6 times 10 to the minus 5th. So this one is more soluble than silver chloride. Yeah, that was the whole point of that slide. Okay, let's see. How does the solubility of silver chloride in water compare to that of silver chloride in acidic solution made by adding nitric acid to the solution? That's important. Because if you acidify it with hydrochloric acid, then you're introducing a common ion. And that's another question. We'll get to that one. But if we acidify it with nitric acid, then the nitrate is just a spectator and we're only interested in the hydrogen ions. Okay. There's our equation. Okay, well, let me erase some of this now. We can draw it again if we need it. So we're back to this one. There we go. So there's our equation, and we want to say what would the solubility increase or decrease or stay the same if we add hydrogen ions? All right. So there's the other equation with the nitric acid, which is a strong acid, so it completely dissociates into hydrogen ions and nitrate ions. Okay. Nitrate ions are not going to react with anything. Silver nitrate is completely soluble, so it has no impact on the equilibrium here. How about hydrogen ions? Well, hydrogen ions could interact with chloride ions, but hydrogen chloride or hydrochloric acid is a strong acid too. So this would have no impact on the solubility. It doesn't change that equilibrium at all. Okay. There are no common ions. So what we're saying is, if this reaction had a common ion, and we looked at that with our Le Chatelier's lab, the common ion effect is how we coupled reactions together. There's no coupling here because there's no chloride here and there's no silver here. And these don't react with any of those products. Okay, silver phosphate. Maybe I should have left that up here. Acidic solution with nitric. So I'm going to leave this one here. And now we're going to talk about phosphate. There we go. And we'll make phosphate over here. A minus, and this is 3. There we go. So how would this affect the solubility? There's our two equations. And this hydrogen, well, the silver and the nitrate, again, is completely soluble. So that has no impact on the solubility. But hydrogen and phosphate, hydrogen plus phosphate, aqueous, yes. Remember when we talked about phosphoric acid? HPO4 2 minus. Which way is this equilibrium favored? Remember, phosphoric acid is a weak acid, even for the first proton. Second proton is even weaker, and the third proton is weaker than that. So it really wants to be over here. That means when you combine this one and this one, you're producing that one. Okay? And that removes this one from that reaction. So we have a coupled reaction with no common ions, but we do have an interaction between this hydrogen and that phosphate, which drags the reaction to the right. We're removing phosphate ions. So that would increase the solubility of silver phosphate. And it doesn't matter what kind of acid you use to get that effect. Now, it does matter if you have an ion in here that will interact with the silver. Like if we had hydrochloric acid, that would make it even more soluble because you're interacting hydrogen with that, chloride with this. So that would make silver phosphate more soluble. But it would also produce a precipitate of silver chloride. That'd be kind of messy. Okay, I thought we just answered that one. No, we didn't answer this one. How does the solubility product of silver phosphate in water compare to that of silver phosphate in acidic solution? It's a trick question.
Yes, I have.
It's exactly the same. The KSP is the same no matter what else you put in there with it. Right? The KSP is this, it talks about this reaction here. If we make the solution acidic, then we're coupling a reaction. We're not changing this reaction at all. So the KSP is the same no matter what you do with it. It's kind of like when we talked about the KW for water. It's always there in an acid situation. Okay. As long as the temperature is constant. If the temperature changes, all bets are off. All right. So calculate the solubility. Now we're going to calculate the solubility of a slightly soluble compound if the environment is modified. All right. So let's make some room here. And let's go back to chloride again. All right, KSP for silver chloride, we had that one before, so I'll write it again. 1.6 times 10 to the minus 10, I believe is. Yeah. Okay, what's the solubility of silver chloride in 100 milliliters of 4 times 10 to the minus 3rd molar calcium chloride? Does the volume matter? We already have the concentration, so the volume doesn't matter. All right, that's blue smoke blown right in your face. Okay. So this initial change equilibrium. All right. What's the initial concentration of silver? 0, correct? What's the initial concentration of chloride? 4 times 10 to the minus 3rd molar. Okay, so now we're going to lose one of these, produce one of those, and one of those, right? Because this is 0. The equilibrium has to move to the right. So we're going to lose change here. We're going to lose some of that, and it's going to show up here as plus S and plus S. This is going to be S. This is going to be S plus 4 times 10 to the minus 3. Now if we write the expression, 1.6 times 10 to the minus 10 equals S times S plus 4 times 10 to the minus 3. All right, let's see. Yeah, there's our ice table. I decided to put the ice table in there. Oh, wait a minute. Hold on a second. My mistake. 4 times 10 to the minus 3 molar calcium chloride. How much chloride is actually added? Twice. Yeah, we have to double it. Set myself up to fail my own exam. There we go. And this is going to be 8. Now, okay, so if we set up the equation, are we going to say that X is significantly, or S is significantly smaller than 10 to the minus 3? Well, the solubility product is this, and half of that, or the square root of that, would normally be 10 to the minus 5th. So even if it were pure water, solubility would be much, much less than this value, right? 2 orders of magnitude less. So I think we're safe to say we're approximately S times 8 times 10 to the minus 3. Okay. That means S equals 1.6 times 10 to the minus 10 over 8 times 10 to the minus 3, right? And 8 into 1.6, let's see. Let's make this 16, so that's minus 9, right? Take one of those. No, that's 11. I made this one bigger, so that one has to get smaller. You see what I did there? I multiplied this by 10, which means this has to go down by another one. Right? That's so I could say this, like that, 8 into 16. And then this becomes a positive 3 in the top times 10 to the minus 8. Right? Okay. So that should be the molarity. Well, there it is. 2 times 10 to the minus 8. You can either do it that way if you want to do it in your head, or you can plug in those values in your calculator and spits out the answer. So how does that compare to the solubility of silver chloride in water? Right? It was 10 to the minus 5th before, wasn't it? Let's see. 1.6 square root. Yeah, 1.3 times 10 to the minus 5. So in water, solubility in water equals 1.3 times 10 to the minus 5. So by having that calcium chloride in solution at this concentration reduces the solubility by 3 orders of magnitude. If you want to keep silver chloride out of solution, that's one way to do it. All right. Yeah, I just threw in that comment. Okay. Calculate the solubility of silver chloride in 4 times 10 to the minus 3rd mole of calcium nitrate. Well, first of all, what is calcium going to react with? Calcium chloride is soluble, right? So calcium ions in solution are not going to affect this. Nitrate's not going to affect that. So the solubility should be the same as in water. 1.3 times 10 to the minus 5. That should have no effect on the solubility. Okay? All right. Okay. The next problem we want to try to solve is has to do with precipitation. In other words, we're going backwards. If we put ions in solution, at what concentration can we expect to form a precipitate? Okay, so what we do is we write the equation, and we have the KSP for the equation, like silver chloride yields silver ions and chloride ions. And we have a KSP for that. Then if we know the concentrations of silver and chloride in solution, say once we mix the two together, then we can calculate a Q before the reaction occurs. If we compare that Q to the KSP, then the precipitation occurs until the concentrations are reduced to the point that they satisfy the KSP. So if the Q is greater than KSP, you will expect a reaction to give you a solid precipitate. If the Q is less than KSP, no precipitate forms. Yeah, if we look at it this way, let's just take silver chloride again. These are aqueous. If we have the KSP, which is equal to 1.6 times 10 to the minus 10, that's equal to the equilibrium concentration of these ions times each other. Then if we calculate a Q, all we need to calculate the Q is the actual concentration of each one. And if this concentration, if this Q is less than that, then what you're saying is that these values are too small. They don't even come up to the KSP. If these values if they give you a Q that's smaller than the K, Q is smaller than the K, what we're saying is, in that case, that these values, the product of these values is less than that needed to produce that. Okay. Now this becomes useful if you have a mixture of ions. Say you have a mixture of metal ions, cations, in solution, and you want to separate them. We go through a procedure called selective precipitation. And what you have to do is choose wisely and in the proper order the additive anions that will precipitate out the ones you want and leave the others behind. Okay? And that has to do with both the concentration of the added cations and the pH of the solutions. So here's, for example, we have barium 2+ and silver ions together. If you add hydrogen chloride, that will form a precipitate with the silver ions, but not with the barium. So if you know you only have silver and barium in that solution, you can separate them simply by adding hydrochloric acid. And you can react the chloride with the silver, drops out of solution, and leaves the barium behind. Now, that gets chloride into solution. What if you use sodium chloride? Well, you could precipitate the silver chloride that way, but that would put barium out of reach because now you contaminated your solution with sodium ions. So hydrogen chloride is a better choice. Let's say we have copper 2+, mercury 2+, nickel 2+, manganese 2+, and we use hydrogen sulfide. Okay. What we find is at a low pH, hydrogen sulfide is relatively, the solubility and the concentration of sulfide ions is relatively low. Right, so at low pH, what we're saying is this: H2S in solution is in equilibrium with hydrogen ions and sulfide ions. Okay. So if we acidify the solution somehow, usually hydrochloric acid will work, then what are you doing? You're adding hydrogen ions to this equilibrium. And if you add hydrogen ions, you're going to shift it back this far. And it's going to use up sulfides. Okay? So if you acidify it, you make the concentration of sulfide very low. And that means that when you calculate the Q with the sulfide concentration and the other metal ions, the value is going to be too low for some of them and okay for others. It just depends on the KSP. If the KSP is very low for a sulfide of one of those metals, and you start off with a low value here, you're likely to precipitate those with low KSPs and leave the others behind. So that's what we're doing. Only the very insoluble mercury 2 sulfide and copper 2 sulfide will precipitate. They have extremely low KSPs. So we get those out of solution and separate them from, right? If we, let's see, the overall K for this one, actually, this is the combination of two, right? Because if it's got 2 protons, it's going to go through losing 1 proton, then losing the second proton. But if we combine the 2, then we can get an idea of what the overall reaction is. And this K is 1.2 times 10 to the minus 20. Very low. Produces very little over here. So if you acidify it, then you're going to drive it back and make the concentration of sulfide ions very, very low. So then once you get the copper and the mercury separated, then you can go to the next step and you would add hydroxyls, right? They would pick up those hydrogen ions and make water, and that would drive the reaction this way and produce a larger concentration of sulfide. Once you got that large concentration of sulfide, now you can pick up the more soluble compounds like nickel and manganese. And this is what the flow chart would look like. And by trial and error calculations, what have you, we need to acidify the solution to a pH of approximately 2. So it doesn't have to be extremely acidic, but slightly acidic will allow you to precipitate copper and mercury from this solution. And then you got left over is the manganese and the nickel, and then you add hydroxyl to get the pH basic, and that'll release a whole bunch of sulfide, and the sulfide then will be high enough concentration to make the Q greater than the KSPs for either of those two. Now you have one solution with copper and mercury and the other solution with manganese and nickel. Then you may be wondering, how do you get the copper and mercury apart? Right? That's another question. All right, so here is a flow chart for separating into categories various metal ions. Let's see, there's one non-metal, there's ammonium's in there also. Separating these cations based upon this sequence of reactions. All right, so if you have all of those ions in there, or if you don't know what ions you have in there, you would follow this procedure. Add aqueous hydrochloric acid. That would separate the ones with very, very low, extremely low KSPs. And that would include the silver, mercury, and lead out of that group. Right? That's group 1. Then you would take that solution and add H2S, right? Hydrosulfuric acid, H2S. And that would take out several others. Copper, bismuth, cadmium. In acidic solution, you've got very low sulfide concentration. So you would take out the metals with the very low KSPs for the sulfide salts. Copper sulfide, bismuth, cadmium, lead, mercury 2+, we did that one already. We did copper also. Arsenic, antimony, and tin. That would be group 2. What's left over, then you would raise the pH to 8, increase the sulfide concentration, and now the sulfide has access to zinc, nickel, cobalt, manganese, and iron 2+. But you've also added hydroxyl, and you see that aluminum, iron, and chromium is out at the same time. That's group 3. Then what's left over? Well, what's left over, if you add sodium carbonate, then you can form the carbonate insoluble compounds with barium, calcium, and magnesium. And then what's left over is the alkali metals, which are all soluble, always and forever, and the ammonium. That's group 4. Group 5, excuse me. All right. You don't have to memorize those if you're worried about it. No. Just recognize why it happens. It all has to do with concentrations of the sulfides, the hydroxides, and how you adjust those concentrations to make the Qs greater than the KSPs. That's the key. The Q exceeds the KSP, you will get precipitation. Now, that's it for solubilities right now. Next, before we go back to solubilities, we're going to talk about complex ions. What is a complex ion? Well, we need some definitions. Complex ions are ions. They're charged species, but they're a combination of metal ions and other things. Like you'll have a metal, for instance, the one we're going to be using is silver combined with the ammonia group. 2 of those with a +1 charge. And this is soluble. It's also very stable. So we would form it by combining this in solution with 2 ammonias in solution to produce that complex ion. And they're all in solution. This part right here, this is called a ligand. When I see the word ligand, I think legs, right? You have the body, and then say it's a spider, you got 8 legs sticking out. These are the ligands sticking out. They're associated with that silver. Now these, we can write stability constants. We can write the, let's see, what's the subscript for this one? Yeah, it does. Yeah, ligand, we use it judiciously in other forms of chemistry. Yeah. Yeah, you can write a K for this expression, and this would be K formation. The formation constant for this group would then be the concentration of this complex ion, right, divided by concentration of silver in solution, and then ammonia concentration to the 2nd power. And that, for that experiment we're going to do when we come back, This is what we're aiming for. We're going to calculate that value for this reaction. Formation constant, sometimes called stability constant. All right. For this example, we're forming a complex ion that eventually is beryllium tetrafluoride. Actually, there's a convention for naming these things. Let's see, do I have a copy of that with me? I thought I did have. Yep, I may not have it with me. But there's a set of rules for nomenclature in these complex ions. I think it's tetrafluoro beryllium 2- ion. I think that's the way they say it. Anyway, when the complex ion is forming here, where the beryllium 2+ ion is taking on ligands of fluoride, it goes through a sequence of additions. So the first fluoride addition has a K value of 7.9 times 10 to the 4th. So what that tells you is the equilibrium is way to the right. That beryllium F with one fluoride is way to the right. Then we take that one and add another fluoride. That one's way to the right, right? The next one's way to the right. And the last one is to the right. Mm. So what that says is each time the new ligand is added, it immediately picks up another ligand and moves the next step. So that overall, adding 4 fluoride ions gives us a K value of 10 to the 12th. You're saying that the fluoride concentration, the fluoride ions are attaching themselves to the beryllium ion in such a way that they're almost completely shifted to the right overall. And you could say the same thing about this process. The first process would be to add 1 ammonia to this, and you get a K value for it. And then you take that product and add another ammonia and get a K for that. Well, the K for the overall would be the one we're looking for here. Okay, there are 2 strategies for dissolving a water-insoluble ionic solid. One we've looked at already, common ions. Right. If you have an ion or coupling reactions, I should say, it's not just common ions, coupling reactions that shifts the equilibrium away from the solid to the solubilized ions. And the other is formation of complex ions. Now, if the anion of the solid is a good base, that is, it goes after hydrogen ions with relish, and it loves hydrogen ions. Mm-hmm. If it's a good base, like the phosphate ion, then all you have to do is acidify the solution, just put hydrogen ions in there, and you'll get more solubility. But if if you have something like this, right, where its equilibrium produces these 2 ions, that is not a good base, right? It comes from a strong acid, so it's a weak base, right? HCl is a strong acid. Its conjugate base is very weak. So acidifying it, we learned already, doesn't do any good. So the option there then is to attack the solubility, not from the anion, but from the cation. And that's what we're doing here. We're removing this cation by forming a complex ion. And that coupling will shift the reaction this way and increase the solubility of silver chloride. In fact, when we do the reaction, you'll see as we're going to do a titration. So as we're doing the titration, you're going to see the formation of silver chloride, and then it goes away because it's forming this here. So those are the two strategies for solubilizing. Oh, am I going to have a video?
First, let's calculate the molar solubility of silver chloride in pure water, and then we're going to compare the solubility that we get in part A to the solubility that we're going to get in part B. And in part B, it's no longer pure water. We're going to have some ammonia present. So we take some solid silver chloride, so that's this over here, and we put it in some pure water, and some of the silver chloride is going to dissolve, but most of it's going to stay in the solid form. So silver chloride is only a slightly soluble compound. So there's my little pile of undissolved silver chloride. But some of it does dissolve, and so we get a saturated solution of silver chloride. So there are silver +1 cations in solution, and there are also chloride anions in solution, and we have our solubility equilibrium. To find the molar solubility of silver chloride, let's go ahead and write down our ice table. So our initial concentrations, our change, and finally our equilibrium concentrations. Before we put the silver chloride in, we didn't have any ions in solution. So the initial concentrations of our product are 0, right? We have 0 for the concentration of our ions. Some of the silver chloride that we put in dissolved. So we lost a certain concentration of our silver chloride, and we're going to call that X. So we're losing a certain concentration of our silver chloride. If we look at our mole ratios, for every 1 mole of silver chloride that dissolves, we get 1 mole of silver +1 cations in solution. So for losing X over here, we're gaining X. We're gaining X for the concentration of silver cations in solution. And since our mole ratios are still 1:1, if we dissolve 1 mole of silver chloride, we gain 1 mole of chloride anions. So over here we get a +X. So at equilibrium, our concentration of silver cations is X, and our concentration of chloride anions is X. So we write our equilibrium expression, and since this is a solubility equilibrium, we're going to write KSP, our solubility product constant, is equal to concentration of our product, so that's concentration of Ag plus raised to the power of the coefficient, so raised to the first power, times the concentration of chloride anions, Cl minus, raised to the power of the coefficient to the first power. So we can plug in our solubility product constant at 25 degrees. It's 1.8 times 10 to the negative 10. So we put in here 1.8 times 10 to the negative 10. And this is equal to, this would be X times X. So this is equal to X squared. So we can get out the calculator and solve for X. So we have the square root of 1.8 times 10 to the negative 10. So we take the square root of that, and X is equal to 1.3 times 10 to the negative 5 if we round that. So X is equal to 1.3 times 10 to the negative 5 molar. So that's the concentration of, let's say, our silver +1 cations in solution. That's also the molar solubility of silver chloride, right? That's how much we can dissolve. So it's a very small molar solubility. So silver chloride is only a slightly soluble compound. Let's see what happens when we have ammonia present instead of pure water. So we have a 3 molar, right? We have some ammonia present now. What happens when ammonia is around silver cations? Right? We get this reaction. So silver cations plus 2 molecules of ammonia give us what's called a complex ion over here. And let's show what's happening. So if we have a silver +1 cation, right, we have 2 molecules of ammonia. So let me go ahead and draw in my 2 molecules of ammonia. And this is certainly not drawn to scale. So I'll draw one in on that side. I'll draw another one in on this side. Remember your definitions for Lewis acid, Lewis base, right? A Lewis base is an electron pair donor. And that's what's going to happen here. The nitrogen has a lone pair of electrons, and each ammonia molecule is going to donate a pair of electrons to our silver +1 cation. Right, so ammonia is donating as an electron pair donor, so this must be our Lewis base. And the silver +1 cation is accepting a pair of electrons, so this must be our Lewis acid. So the formation of a complex ion is a Lewis acid-base reaction. And notice the equilibrium constant for this, 1.6 times 10 to the 7th. Kf is called the formation constant. This is a very high value for the equilibrium constant, right? So the equilibrium lies to the right, and this is a stable complex ion. So any silver ions that are in solution, if you have ammonia present, ammonia is going to pick up that silver ion and essentially remove the silver ions from solution. So if we go back up here and think about our equilibrium, right, if we have ammonia present, we're going to be removing silver cations from solution. Right, so we're decreasing the concentration of silver cations. We're decreasing the concentration of one of our products. And Le Chatelier's principle says if we're decreasing the concentration of one of our products, our equilibrium is going to shift to the right to make more. Therefore, increasing the solubility of silver chloride. More is going to dissolve because the ammonia is present, because of the formation of our complex ion. So if we added some ammonia, right, if we added a solution of ammonia here, we could get our silver chloride to dissolve, right, because it's more soluble because of the formation of a complex ion. So let's say we add enough ammonia solution where we get our silver chloride to dissolve here. So that's the idea. Adding our ammonia, right, caused formation of a complex ion which increased the solubility of our silver chloride. So we would expect an increased solubility here of our slightly soluble ionic compound silver chloride. And next we're going to do the calculation. We're going to find the solubility of silver chloride in our 3 molar ammonia solution. Now we've looked at two reactions. We've looked at the solubility equilibrium for our slightly soluble compound, and we've also looked at the formation of our complex ion. Now let's add those two reactions together to get our net reaction for what's happening. Right? So we're going to add our two reactions together to get a net reaction for what happens when you put silver chloride in ammonia. Right, we have silver cations on our reactant side and on our product side, so we can take those out. And so for our reactants, for our net reaction, we have solid silver chloride plus ammonia. And for our product side, we would have our complex ion and our chloride anion. So we have our complex ion, and we also have chloride anions, so Cl-. So that's the net reaction, and if we added those two reactions together to get our net reaction, we have a new equilibrium constant, which I will call K. And if you add two reactions together to get your new equilibrium constant, you multiply the equilibrium constants of those two reactions. So K is equal to KSP times KF. So if you did that calculation, 1.8 times 10 to the negative 10 times 1.6 times 10 to the 7th, you'll get your new equilibrium constant. And I won't do it here just to save some time, but if you do that, you'll get 2.9 times 10 to the negative 3rd. So that's a 9, 2.9. All right, our goal is to find the molar solubility of silver chloride in our ammonia. So we set up our ice table, so our initial concentrations, our change, and then our equilibrium concentrations. And let's pretend like we're starting out with our solution of ammonia and we haven't added any silver chloride yet. So let's go back up here and let's see what our concentration was. Well, we started with a 3 molar solution of ammonia, so let me put that down here. So our initial concentration for ammonia is 3 molar. And if we haven't added any of our silver chloride, then we don't don't have any of our complex ions. So the concentration, the initial concentration of our complex ion is 0, and we also wouldn't have any of our chloride anion either, so that concentration would be 0 too. So now we add our silver chloride to our solution of ammonia, and some of our silver chloride is going to dissolve, and so we make that concentration X. So we're losing a certain concentration of silver chloride, so we write minus X. Next, we look at our mole ratios. So the mole ratio of solid silver chloride to ammonia is 1 to 2. So for every 1 mole of silver chloride that dissolves, right, we're also going to lose 2 moles of ammonia. So we write minus 2x here. For our products, if 1 mole of silver chloride dissolves, we make 1 mole of our complex ion. Right? So if we're losing X over here, we'd be gaining X over here for the concentration of our complex ion. And same thing for the chloride anion, because our coefficient is a 1. So we're going to gain X for the concentration of chloride anion. So at equilibrium, our concentration of ammonia is 3 minus 2x, our concentration of complex ion is X, and our concentration of chloride anion is also X. Next, we write our equilibrium expression. So K is equal to concentration of products over reactants. So I look at my complex ion over here, so concentration of our complex ion, and we raise the concentration to the power of the coefficient, so to the first power. This is times the concentration of our chloride anion, so times the concentration of chloride anion raised to the power of the coefficient, so raised to the first power. We also have some reactants here. So we leave silver chloride out because that's a solid, right? But we have ammonia. So this is all over the concentration of our reactant. So this is over the concentration of ammonia. And notice our coefficient is a 2. So we need to have a 2 here. Next, we plug in our equilibrium concentrations. So our equilibrium concentration of ammonia is 3 minus 2x, our equilibrium concentration of complex ion is X, and our equilibrium concentration of chloride anion is X. So on the right side, we would have X to the first power times X to the, let me take that out, times X to the first power. Right, all over 3 minus 2x to the second power, so squared. And then we can plug in our equilibrium constant k, which is 2.9 times 10 to the negative third. So 2.9 times 10 to the negative 3 is equal to, on the right side, we would have x squared. So let me write this out. We would have x squared over 3 minus 2x squared is equal to 2.9 times 10 to the negative third. And so what we could do here, these are both x squared, right? These are both x squared, so we could just say that this is all squared on the right side. And then we could take the square root of both sides, right? So take the square root of 2.9 times 10 to the negative third, and take the square root of what's on the right. So the square root of what's on the right would be x over 3 minus 2x. And let's take out the calculator to do the other one. So square root of 2.9 times 10 to the negative third is equal to, let's round that to 0.054. So it just makes it easier here to round that. So 0.054. Our goal is to solve for x. Our goal is to solve for the molar solubility. So we can multiply both sides by 3 minus 2x. So when we do that, right, we would have this. So we need to multiply 0.054 by 3, and if you round that, you're going to get about 0.16, and 0.054 times 2 is approximately 0.11. So we have 0.16 minus 0.11x is equal to x. So we have 0.16 is equal to, we put both x's on one side. This is 1x, and this is 0.11x. So 1x plus 0.11x is 1.11x. And so now we need to solve for x. Right? So we've done our math here. So we have 0.16. We need to divide that by 1.11, and that is equal to 0.14. So x is equal to 0.14, which is only approximate because of all the rounding that we've done. So this is concentration, right? So this is our molar solubility. If we go back up here, x equal to 0.14 molar, All right, so that's our concentration of complex ion in solution at equilibrium. That's our molar solubility of silver chloride. All right, so it's 0.14 molar. Let's go way back up to the beginning and compare the molar solubilities. Right, so in pure water, the molar solubility of silver chloride is 1.3 times 10 to the negative 5 molar, which isn't very soluble at all. But now we have ammonia present. We've increased the solubility, and we just calculated the molar solubility is 0.14 molar. And obviously 0.14 molar is a lot larger than 1.3 times 10 to the negative 5. So the formation of a complex ion increased the solubility of our slightly soluble compound, silver chloride.
Okay. Now, in order to form this complex ion, you have to have a lot of ammonia in solution, like 2, 3, 4, 10 molar ammonia in solution in order to do that. So there's our, and that, I don't know why it does that. It puts a box in there instead of a double arrow. I think it's missing a font. Yeah. But use your imagination. So there's the solubility product for that reaction. And then this is the first addition of ammonia to the silver, right? And its K value is 10 to the third, so it's way to the right. And it forms a complex ion with only one ammonium. But then as soon as that one forms, we tack on another ammonia with even a greater K value. So the combination of, let's see, we're going to combine all three of them or just the two? Since the complex ion formation equilibrium lies far to the right, virtually all the silver ions produced from silver chloride are converted to, yes, to diamine silver plus. As a consequence, the composite of the three reactions above is the true situation in the solution. Because all this is happening in the solution. All these ions are there together in the solution. We've only separated them here to help us understand what's going on. But in the solution, I mean, they don't care, right? That's nature just does what it does. Right, so if we combine those reactions, we get silver chloride plus 2 ammonias yields the complex ion plus chloride ions. And what's the K for that? Well, the K for that is the product of each of those Ks. And that's 2.75 times 10 to the minus 3. Right? Well, how about that K? The K is larger than the KSP. And we don't have any, well, we do. We do have the power of ammonia is squared. So we can't say a whole lot about solubility without calculating it. Is that what we're going to do? The KEQ then is 2.75 times 10 to the minus 3, all right? And yeah, the ammonia concentration has to be high in order to satisfy that K value. I don't remember what concentration we're using. Is it 2 or 3 molar, something like that? Okay, so let's say we want to solubilize silver chloride, and we say X is the solubility of silver chloride, and set up the ice table based upon this reaction where we're forming the complex ion. Okay? So if X is the solubility, right? I don't know if this will help any. 320. We're good till 5, aren't we? Yeah. Okay. I hope I won't have to take all of that time. Mm-hmm. But if we combine that equation and we get 2 ammonias And then we get the complex ion. Plus chloride. Right? Then we set up our ice table. And we say we're going to fix the concentration of ammonia at 10 molar, which is really high. When you add that to the solution, you will smell it. Right? It will, right? It'll knock you down if you get your nose too close. And initially, we start off with none of this and none of this. Right? So we know the reaction's moving to the right. So the solubility then is in terms of this one. The change is the solubility is S. And for every one of these S's, you have to lose two of these. Right? Because the ratio is 1 to 2. So for every one soluble unit of this, you lose two of these. But you only gain one of these. And you gain one of these. Right? So this is 10 minus 2S, and this is S, and this is S. So if we use that KEQ, which was calculated for this situation using those three different Ks, then the KEQ is equal to 2.75 times 10 to the minus 3. And I'm not going to write the rest of that stuff up there. But if we take this one, S, this one, S, and then down here we have ammonia squared, 10 minus 2S squared. That would be your expression for finding the solubility of silver chloride when you have a 10 molar ammonia solution added to it. There we go. Now, the nice thing about this is because this is S squared, right? S times S is S squared. We can factor out the square and we can say S over 10 minus 2S. The whole thing is squared. Okay? So what does that mean? If this is squared, then if we take the square root of this one, 2.75 times 10 to the minus 3, then that's equal to S over 10 minus 2S. Right? We just took the square root of both sides. And that makes it easier to solve for S. We don't end up with a quadratic. All right, if we keep working our way down, I had to go to the next slide. Keep working our way down. Right. Then we get the square root of this times this value. And it's a matter of solving for the unknown from that point on. Right. And that's what these manipulations are doing. We find out that now the solubility of silver chloride, S, equals 0.47 molar. Right. That is huge compared to, what was it, 1.3 times 10 to the minus 5 in just pure water. Right. So just adding that ammonia will get the silver chloride into solution. Let's see. That side calculation just tells you how much ammonia is left. Right? How much ammonia did we lose? What concentration of ammonia is left? We started off with 10, but 2 times this subtracted from 10 is 9.06. So we lost a whole molar of ammonia to make this reaction go. That's what that right-hand calculation tells you. That's it.